In this video, I explored the concept of turbine control, focusing mainly on torque and pitch control, with a more detailed discussion on torque control. Let's dive in. First, a quick reminder about horizontal axis wind turbines. This type of turbine typically has three blades, each consisting of multiple aerodynamic airfoils. Each blade is connected to the hub through bearing, allowing the individual rotation or pitching of the turbine. The airfoil generate aerodynamic lift and drag forces, and the lift force acting at a distance from hub produces aerodynamic torque which rotates the blades. The rotor system is connected to an electrical generator through a shaft and gearbox, converting mechanical rotational energy into electrical energy. Let's first answer why the turbine control is important. The main objectives of wind turbine control are to maximize energy capture, protect the turbine from loads and damage, and ensure stable, reliable power output. Here I'm listing a few of objectives. Maximizing power production for below rated wind speed. Here the controller operates the turbine at the optimal tip-speed ratio and adjusts generator torque and rotor speed so that the turbine extracts as much energy as possible from the wind. Limit power at high wind speeds for above rated wind speed. Once rated power is reached, the controller prevents overproduction, using pitch control to reduce aerodynamic efficiency and keep output near rated power. Third objective is to reduce structural loads and fatigue. We know wind is turbulent. It creates fluctuating loads on blades, tower, drivetrain, and bearings. Control systems reduce these dynamic loads to extend turbine lifetime and lower maintenance costs. The controller also maintains safe operation by protecting turbine against extreme conditions such as storms, overspeed, grid faults, vibration, and overheating. It includes emergency shutdown, braking, and cut-out operation at very high wind speeds. The controller optimizes power quality and grid, and also minimizes mechanical stress and noise through smoothing control actions and reducing drivetrain torsion and blade vibration. In this video, I explain very briefly on two control strategies, namely torque control and pitch control. I then focus in more detail on torque control. But before diving into those control systems, it's important to remind the power curve. In this curve, in x-axis, we have wind speed, and vertical axis is the power of a 5 megawatt wind turbine. In region 1, color-coded by red color, below a certain cut-in wind speed, we have no power production. above cut-in wind speed and below a certain rated wind speed coded by blue color, we have power production proportional to wind cube and estimated through this relation. For a turbine with radius r, here rho A is air density, V is relative wind, and Cp is the efficiency of the turbine or power coefficient, which is a function of tip speed ratio lambda and blade pitch angle beta. Lambda is defined by linear speed of rotor omega r multiplied by radius of rotor swept area divided by the relative wind V. In region 2, the controller adjusts generator torque and rotor speed so the turbine could extract as much as energy as possible from the wind. In this region, we assume no pitch and pitch angle beta is kept 0. In region 3, above rated wind speed, coded by green color, the controller tried to prevent overproduction using pitch control or rotating blades to reduce aerodynamic efficiency and keep output near rated power. Here I present an example of a steady-state wind turbine performance in region 2 in this figure. Between cut-in and rated wind speed, the tip speed ratio reaches to its optimal value and the controller regulates torque to maximize power production. This means the rotor speed is controlled to remain proportional to wind speed, as shown here by blue dotted dashed line, ensuring operation at optimal efficiency point. The thrust force increases with wind speed, shown by green dashed line, and reaches a peak near the rated wind speed. Once pitch control, shown by dashed red line, begins in region 3 above rated wind speed, the thrust force decreases as blade pitching limits aerodynamic loading. Wind turbine designers often aim to reduce this thrust peak slightly below rated wind speed. In region 2, both rotor speed and power increases with wind speed, while in region 3, power is maintained nearly constant. As pitch control becomes active. As I mentioned in this video, I focus more on torque region control in region 2. Each wind turbine has a diagram called Cp lambda power coefficient tip speed ratio curve, where the horizontal axis presents lambda wind speed ratio, and the vertical axis represents Cp or power production power coefficient for different blade pitch angle beta. As shown in region 2, at zero pitch angle, Cp increases with lambda until it reaches an optimal tip speed ratio, lambda opt, where Cp attains its maximum value. Beyond this point, Cp decreases, and I should say that these curves are estimated using blade element method. The control objective in this region is to regulate generator torque so that the turbine operates at optimal tip speed ratio to maximize energy capture. In optimal tip speed ratio, lambda opt and maximum power coefficient, Cp max, we can estimate the power production, and in power production, using definition of lambda, we estimate and replace the wind speed in power formula, resulting in this formula as shown here. Since power is defined by torque multiplied rotational speed, we have the torque formula as shown here. We see here instead of wind speed, we have rotational speed of the rotor. As shown in this figure, on the generator side, we have generator torque, Qg, and generator rotational speed omega g. We defined capital G as ratio between omega g and omega r. We aim first to obtain a relation for the generator torque for the optimal tip control condition. Using conservation of energy, for ideal case in the absence of all losses in a steady state condition, we obtain generator torque as given by this formula. After deriving the relationship for QR and QG in previous slide, we derive now the rotor dynamic equation for unsteady condition using Newton's law, as force is mass multiplied acceleration. For rotor speed of omega r, acceleration is time derivative of omega r, as shown here, and mass is rotational inertia, id. In the absence of loss mechanisms, including, for example, losses in the gear transmission system for the rotor generator system, as shown in this figure, we have then this relation. Now, if we insert the aerodynamic torque and optimal tip speed ratio and QG for the optimal tip speed ratio condition estimated in previous slide, we get the dynamic equilibrium of the rotor speed as shown in this equation, and then this equation. The control objective, as shown here, is to adjust rotor speed to keep the rotor speed ratio at its optimal value. If bracket value is positive, the rotor speed increases, while when it's negative, the rotor speed slows down. There are other methods that can further improve this simple control approach, which are not discussed here.